Good morning. Could you confirm that you see and hear me?
Sì, professore.
Grazie. So let's move towards a conclusion of the part addressing ideal rocket nozzles. And about ideal nozzles, what we have seen, and just would like to summarize here, is that the main performance parameters that measure the nozzle performance is our thrust coefficient. And so why this is something so that measures the performance of the nozzle, that is let's say the energy conversion component that we have in all thermal rockets. And this parameter should be possibly high. It means that high performance means also high thrust coefficient. So why this should be high, and what is the interest in having this thrust coefficient high? Of course, we have as a reference thrust and specific impulse. So recall, thrust is the goal that we have to achieve, and specific impulse is the quality that we have in achieving this goal. That means how much propellant we need to have to get a given thrust level for a given time. So in terms of thrust, having high values of thrust coefficient means that you can obtain the same thrust with a smaller or lower pressure engine, because we recall that thrust is thrust coefficient, total pressure, and thrust area. So if the value of thrust coefficient is higher for the same thrust, it means that P0AT is smaller. That means at least that you save some engine weight, because it's something at lower pressure or at of a smaller size. On the other hand, if we look to the specific impulse, we record that we have ISP C star CF, where C star is the characteristic velocity representing the energy that we have available within the propellants. And we see that for a given value of C star, having high values of CF means having high values of specific impulse. So it means that increasing thrust coefficient increases the specific impulse. It means that lowers the amount of propellant we need to achieve a given mission. We have so looking to this parameter, we have found that at given, let's say, altitude, so for a given value of PA, the atmospheric pressure, and for a given value of total pressure, we have found that the best, so given P0 and PA, it follows that the best thrust coefficient, the maximum value, is when PE equal to PA, when we have adapted nozzle. But this is for a given P0 and PA. But our rockets never work in adapted condition in general. So because we are operating in vacuum and we are not able to adapt up to vacuum, it would be infinite pressure ratio, infinite area ratio. Or if we are not working at vacuum, we are working in with changing altitude. So we are in the ascending phase. So what we do? Vacuum. Just to recall what we said. We would like to get maximum thrust coefficient, so we should close as much as possible the adaptation value at vacuum. And this is done adapting, let's say, so considering an expansion ratio and adaptation altitude as high as possible. That means adaptation pressure as low as possible. Means that we should get maximum, and we have seen that thrust coefficient is just a function in vacuum, just a function of gamma and epsilon. So, and it's increasing function of epsilon. So we should move towards as high epsilon as possible, as high error ratio as possible. So what means as much as possible? It means that we would like to increase this epsilon, provide that this increase do not add engine weight more than the propellant mass which is saved. So of course we have to consider that at a given point we have an asymptotic value, thrust coefficient is no longer increasing so much, and so the specific imparts, and so the saving of propellant, whereas we have, let's say, something more linear or monotonic for the increase of mass with increasing expansion ratio. So we can note for the vacuum operation that increasing pitch zero, so working at higher pitch zero, means that we can achieve the same expansion ratio in a smaller volume, and this can be something interesting for the applications, because in an upper stage you have not infinite room available, you have a limited space that you can occupy, and having high total pressure would allow you to have a more compact engine and achieve the desired high error ratio even in, let's say, in a smaller available volume. So then we pass to the ascending phase. So for application related to the ascending phase. So also in this case, the question is what will be our epsilon, what will be our PE, the expression. And here what we have seen is the behavior of thrust coefficient as a function of the altitude, and we have designed here for a given pitch zero a line showing the adapted value of thrust coefficient, which is the maximum at each altitude. But in general, what we have to consider is a fixed geometry, that means fixed value of epsilon, and so a fixed value of pitch zero of PE. It means that we have to identify where that we will be adapted only at a single altitude when PE is equal to PA, and then we have to identify what will be the best altitude where we can optimize, we can adapt to optimize our mission. So of course we can imagine that if we are working, let's say, in this range, so from this altitude to this one, we can imagine, let's do something in the average. And so if we plot this is a line relevant to a given epsilon, is always less than the adapted value, as you see, and we'll have a point, let's say, at half altitude, where we have selected our adapted condition. Yes, this can be a solution. can be also that we say that at the given point we have separation, and if we have separation, we have also a sort of adaptation here. We leave this line, and we have some, let's say, we no longer consider a decrease. We no longer have a decrease of the trust coefficient because of the further increase. I'm moving from right to left of the ambient pressure. So this is a possible case, but there are also other. And depending on the value of this Z1, of this Z1 half, that is not a rule. Of course, there will be some optimization, but just to have to say, let's do something. We take as first tentative value the one which is at the middle of the initial and final value of ambient pressure or of altitude. We can, of course, it's not linear, so it depends on what you choose, and so on. So this is why you should optimize in general. But what you find, even looking to this simple picture, what we can say is that if this Z1 is not so high, you'll have a limited, let's say, change of thrust coefficient during the whole operation. Of course, the more you are moving towards high altitudes, the more this difference will appear. And if you try to optimize the given point, it means that if you consider a core stage, a sustainer stage that will operate from sea level up to orbit, let's say, or up to very high altitude, and it will spend most of its life in vacuum condition. So if you balance time spent at low altitudes and the time spent in vacuum, you will find that your optimization will tell you that you should optimize for the vacuum conditions. And this means that the design should be like the design for the vacuum engines. So as much epsilon as we can. And here comes the point I would like to mention today, or to recall today. So we have two possible applications. One is first stage or booster, typically working a couple of minutes and always within the atmosphere. That is, even if with decreasing ambient pressure, but let's say we don't reach vacuum condition. And another application is that of sustainer or core stage, or ideally a stage of an ideal single stage to orbit launcher. That is operating all along the trajectory. So in this second case, most of operation will be in vacuum, and so we should adapt as done for the vacuum case. The problem is in this case that if you move in this plot, you should move and say something. Possibly here to adapt to a very high altitude, and you'll have something like the dashed line I'm plotting here. So this is always increasing. I mean, there is, in the under-expanded regime, there is always some increase of thrust coefficient, even if this is lower than the adapted value. So what happens here? You see that this line is going down quickly, and at a given point, what happens is that we have flow separation. And it will continue to in this way. So it seems that it's not too bad because we can achieve, let's say, we have a loss in the at low altitudes, but still we can achieve very high area ratio and so good performance in vacuum. Consider that if I put another kind of nozzle, let's say adapted here, I would have something like this. So that you find it's less than the other. For we have this gap that in one case it's at low altitude and in one case it's at high altitude. So if you spend more time at high altitude, of course, it will be convenient to consider the higher expansion ratio. So the problem is now focusing on this overexpansion here at sea level that bring us to work in such overexpanded condition that we have flow separation, which is represented by this dashed dot line. So the problem is that in practice, no engine that has been realized so far allows us to work at steady-state conditions at liftoff with overexpanded conditions such that we have flow separation. So we avoid flow separation in the steady-state condition. So flow separation at sea level must be avoided. And what is the reason? Or at least, let's say, controlled or controlled. What is the meaning of this word, of this reasoning? Is that when you are considering now your separated flow here, we have commented this operating condition, saying that there will be a separation, for instance, at this point here, and we have that the flow detaches, that we have an oblique shock, and so on. This is, of course, something that will occur all around the nozzle cross-section. So what we imagine is if this is the trace of cross-section, we'll have similarly this separation here. So what happens is that actually this point, when you see the pressure behavior and we have something like this along the abscissa, with here we have the separation and we reach more or less the ambient pressure. Of course, this will go down from higher values. What we find is that if we have changing of values of the ambient pressure, or let's say of the pressure inside this region, accordingly this separation point will move. For instance, in this way or in this way, with this range of oscillation, the flow separation point will move. And here we have this separated flow, which actually is not so smooth. We have some fluctuations that must be taken into account, and they are such that typically what happens is we have separated flow. This position is not the same, it's not fixed all around the nozzle, but will be oscillating. And so if it is oscillating here, and at any point all along the cross-section, we have something that nobody can guarantee that we have at zero resulting force in the peripheral direction. So what we have here is, let's imagine an extreme case where everything is oscillating, let's say, as together. So we have, for instance, that this point is oscillating and is here and here, because this should be theoretical, but this point has moved in this direction at the same time, and this is moving at this position, and all is moving together. We can identify a separation plane here, and so you see that if you look to pressures on the walls, we have different pressure if we consider now this part. Here we have that, here we have a low pressure. Here you have low pressure. And on the other side you have ambient pressure. So this will be less than half the pressure that we have on this other side. So as a result, we have a resulting force in this direction. And we refer to these forces as side loads. And this will also be a bending force that will act on the nozzle. So usually we don't design this nozzle to be an increased weight to make it resistant to these forces that are also oscillating, so it's also a dynamic load. And therefore, this is the reason why we like to avoid flow separation during the whole time of operation of our rocket. So the main reason is to avoid this fluctuation that results as side loads that will make us make more complicated the design in terms of structural loads and weight. Actually, we have that something may happen, but for a short time during the startup phase, where we are for sure, as pressure is increasing, we will reach during this transient overexpanded condition. But usually the critical conditions occur for a short time, and this can be, of course, this must be accepted, and is of course less complicated to deal with than considering a design condition with separated flow at sea level. So going back to the last plot I shown in class last Wednesday, we had thrust coefficient as a function of epsilon, and this is a very useful diagram because it allows us to identify different conditions and different performance that can be achieved by different nozzles at different chamber, or say chamber total and ambient conditions. So what we find is that for a given P0 over PA, we have something like this with a maximum value. This means that we have a given value of P0 over PA. And we have an adapted condition here to this epsilon, and this corresponds to having PE equal to PA. And we found that we can draw many lines like this on this diagram, and each corresponding a different value of P0 over PA. And in particular, we are moving with increasing values in this direction. And we also found that we have our maximum value that corresponds to adaptation to vacuum. So we identify here the line of maxima. That is the adaptation line. So adaptation to vacuum is here. And these boundary lines is the performance that we have for a given value of epsilon in vacuum conditions. So here we have PE equal to 0 along this line. This is PE equal to PA. And different lines correspond to different ratio P0 over PA. So we see, for instance, that we are adapted this epsilon for this P0 over PA and have this trust coefficient. So if this is done, this line is realized by considering that this quantity is constant and we are changing the nodes are considering different expansion ratio. You recall that I said let's consider or not more or less of this line along the nodes, so make it longer or shorter, higher or lower expansion ratio. So we can, we know that following this line, we reach a point where we have flow separation. And the same is true for all these lines. And it's similar to what we have here, PE equal to PA. We will have another line, this one, where let's say could be PE equal to point something 3 PA, 0.25, 0.4 PA. And this is the line where we have flow separation. That I say that ideally should be that at this point we have no longer changes of trust coefficient if we change epsilon, if we further increase epsilon, but in the real case we have something that is decreasing because of the flow motion we have here in this region here. That becomes a larger and larger region where these losses will be higher. We have something that is less of the ambient pressure in that separation region, and so we have this kind of lines. So over this plot, we can at this point see following this line is just something that allow us to see what happens changing epsilon, but this is something that you don't do usually. What you do is that you assign a given value of total pressure, you find an adaptation altitude, and then you change your ambient pressure during trajectory. So typically what we are considering here is a given epsilon. Let's say this one. This is a given geometry. And what happens here? So if you have a given value of P0, so you know that, for instance, and of course you are considering that trajectory will begin at sea level. What you see here is that at this point, for this epsilon, we have, let's say, if we have selected this epsilon because we like to adapt at this altitude, and we can, or let's do a different reasoning. So let me remove this line that it's better to work in this way. So we know that, for instance, this P0 over PA, this is the ambient pressure at sea level, and this is our design total pressure. So to achieve the maximum, if these are the values of pressure that I have to deal with, to achieve the maximum performance during vacuum operation, I should achieve the maximum epsilon that is allowed. And in this case, is this one. before we have flow separation. So we start here at this epsilon. This is our maximum epsilon for our P0 starting from sea level. And so at this point, what happens is that during trajectory, we will work in overexpanded condition up to this point, and we reach this value of thrust coefficient, and then we move in the underexpanded regime on the second part. So we move in this direction along the trajectory with increasing thrust coefficient at a fixed value of epsilon. On the other hand, you can see that if we consider now a value of total pressure which is higher than the former one, so we improved our design of the engine and we are able to work at higher ambient pressure, higher total pressure, we will start now at this point. That means we are able to move towards a higher value of epsilon. It will be this epsilon 2 around 2 P02 over P0 over PA, and this is P01. And so now we will work along this line, and we see that we are now adapting a higher altitude. So this is also how you can read this plot, and also you can identify, of course, on the left and right of this dashed line here. You find on the left, you find the underexpanded condition, on the right, the overexpanded conditions. Well, I imagine that some of you can have in mind the question why you are considering constant P0. Because we have our thrust coefficient, and in principle we have for a given P 0, we have let's say we like to adapt at this altitude here, and we have our thrust coefficient once again. So what you see here is that this is what we obtain at constant P0. But if we increase in, let's say, if this is the adapted condition, and we increase chamber pressure according to the atmospheric pressure, let's say, we have a higher pressure at sea level, so that we have that the exit pressure will be equal to the ambient pressure. Then as the ambient pressure decreases, I will also decrease the total pressure, and so I will always work in adapted condition up to this point. I work this way. So this is with changing P0. But notice what is the disadvantage of working in these conditions. Once you are able to design your nozzle to work at this total pressure, actually you can work at this pressure all along the trajectory. And because and of course it will not be this line. This is the P0 prime, which is a higher pressure. We will follow this line. This is the always adapted condition, but you will follow a new line, which is this one, because you are adapting at sea level, and will be something less. But you see that this something less is always more than what you have in the former case. So if you are able to work at a higher pressure, it's better not decrease it if you are looking for the best performance. So after this summary of thrust coefficient of ideal nozzle, I would like to tell you, to give you some more information about we move from ideal, when we move from ideal to real nozzles. So you recall that we made many assumptions at the beginning of this discussion, and if we say nothing about our C star, we can say that everything we mentioned before about thrust coefficient is based on one-dimensional theory, for instance, and isentropic and so on, single phase, so many assumptions. So let's try to remove some of them. In fact, we already removed the isentropic conditions when we talk about the occurrence of the normal shock. We also removed the assumption of one-dimensional flow when we talked about flow separation. But in general, we are assuming that we have a relation between cross-sectional areas and pressures, and we never specify that this is the pressure at the axis of the engine or at the wall. We are always assuming that it's one-dimensional flow. And actually, when we write also the epsilon 1 over m, 1 plus delta m squared, 1 plus delta gamma plus 1 over 2 gamma minus 1, we write this, or we write gamma over square root blah blah. We never say anything about how the area is changing with the axial position. So we never say what is the A or the X, also for the one-dimensional flow. So actually we don't consider the variation along the axial direction, so that we can consider something like this or something like this with the same area here, if this is equal to this one. For our theory, for so far, these two nozzles are identical. These are, for instance, the reference that we can do is for a conical nozzle, so we have a constant slope for our diverging section. But we have to imagine here now that the flow will follow wall. If we have no separation, we have to expect that flow follows walls. And here you see that velocity will be in this direction, whereas in this case, in this direction. So you see that here is less one-dimensional, the exit flow, and less one-dimensional means that we have also to consider components of velocity in the radial direction, or even if we have azimuthal symmetry, so we can consider axisymmetric flow, we have that in principle the more the diverging angle, the more will be the component of flow velocity at the exit of the engine. The more will be higher the component, the radial component of velocity at the exit of the engine. So what is this, the role of this component? Imagine that you have reached an absolute value of velocity. So at this point you have that the same velocity can be in this direction or turned of an angle. And you see the higher the angle, the lower will be the component in the axial direction and the higher in the radial direction. Of course, when we made the balance of momentum that allow us to evaluate the forces acting within the nozzle, and so the resulting thrust that we generate, we only made the balance in the thrust direction, that is the axial direction. So reducing the velocity in the axial direction and thus the momentum in the axial direction will also is, let's say, one information that tells us about the reduction of the thrust due to this shape, so due to the fact that we have some higher component in the radial direction. So we have to consider in general this that will be referred to as divergence losses. So it means that in the momentum balance, only the component in the thrust direction matters. And here we are distributing part of momentum in a direction, the radial one, where it provides no contribution to thrust. And of course, there will be, this is also clearly in the case of axisymmetric flow, you have that the same momentum is in all directions, and so at the end it will be a resulting force of 0. Of course, you have to imagine that we have a component of velocity and so a momentum in all directions, and so overall the resulting force will be 0. So to take into account this, what we do, we correct our one-dimensional expressions. And in particular, here we say that our thrust coefficient will be this lambda by the ideal value. And this lambda is just a correction of thrust coefficient to take into account divergence losses. And for a conical flow, provide that the angle is not too high and the length is sufficiently greater than the trough diameter, you can approximate this loss with the following formula that we can write here as 1 plus cosine alpha divided by 2. And this alpha is this angle here, is the angle of the cone. Well, this is not the only correction that we may consider. There are also other that take into account the friction, the heat transfer, possible occurrence of condensed particle, of chemical reactions, of thermally perfect rather than calorically perfect gas, and so on. What we do is to introduce, of course, an ideal computation and then some efficiency in terms of thrust coefficient, characteristic velocity, I mentioned also this here, and specific impulse. Which are the values measured with respect to the ideal ones and that are typically less than 1. Well, we can stop now, and 10 minutes will continue shortly on this, and we will go back to the divergence losses in at 110.
Professore, scusa, fare una domanda?
Sì, certo.
Ma nel momento in cui definiamo l'efficienza del coefficiente di spinta, le perdite per divergenza sono incluse o meno? Cioè, nel senso, sono due cose separate, o nel momento in cui definiamo l'efficienza abbiamo incluso automaticamente le perdite per divergenza?
Diciamo, nell'ETA ci sono, cioè ovviamente il coefficiente di spinta ideale è uno, è quello che abbiamo definito nel caso, diciamo, per quello di cui stiamo parlando adesso, diciamo così, è il caso isentropico con calori specifici, diciamo caloricamente perfetto, e quindi è un ben definito numero per un certo rapporto d'area. E il CF che c'è al numeratore di quelle da CF va letto come quello misurato, non quello che risulta realmente, per cui all'interno di questo eta CF c'è sicuramente anche, ma non solo, il lambda, cioè la perdita di divergenza.
Ok, perfetto, grazie.
Prego.
Posso farle anche una domanda?
Certo.
E volevo chiedere, nel caso, quando stiamo parlando della quota di adattamento del nozzle, quando parliamo per esempio di un secondo stadio, la pressione di uscita del nozzle conviene che sia, cioè che la pressione di adattamento del nozzle sia più bassa della pressione a cui, diciamo, dovrebbe accendersi il secondo stadio, o che sia comunque più alta, in modo che si adatti dopo? Il contrario, volevo dire.
Sì, vabbè, comunque il discorso è chiaro che è analogo a quello del primo stadio. Il fatto in realtà è che quando siamo al secondo stadio già iniziamo ad essere a pressioni sufficientemente basse, e quindi diciamo che il problema dell'adattamento riguarda soprattutto il primo stadio o l'unico stadio nel caso di propulsore di lanciatore monostadio. Però in generale sì, il discorso è analogo. È chiaro che se abbiamo un secondo stadio che inizia le sue operazioni a determinata quota e funziona ad esempio fino al vuoto, o spende gran parte del suo periodo nel vuoto, bisogna cercare da questo punto di vista, ovviamente, perché quel sistema è complesso, però da questo punto di vista vorremmo certamente spingersi verso un adattamento nel vuoto, e quindi il rapporto di espansione massimo tollerabile, il che vorrebbe dire di andare nella condizione di funzionamento sovraespanso a quella specifica quota di inizio operazione. Sovraespanso, ma per gli stessi motivi per i quali non vogliamo i carichi laterali nel primo stadio, non li vorremmo neppure, a maggior ragione, nel secondo.
Va bene, grazie mille.
Prego. So let's continue, and let's start from what also based on one of the questions that were asked during the break. Why we are highlighting these divergence losses if they are included in all other losses? One reason is that of course, to highlight the fact that we have to define a shape and the length of the nozzle. And another reason is that this shape and length are evident in the nozzle design, and you see, or also in the nozzle images. So that means that the control and the improvement of performance with respect to these divergence losses is quite important and characterize our nozzles. Actually, this shape is such an important aspect that actually it's what defines at the end the possible performance that we can achieve for a given, let's say, one-dimensional ideal operating condition. So, in fact, what you see in practice is sometimes you see some conical nozzle, but in general, so of course these are conical nozzles, but usually what you see is what we call bell nozzle or contoured nozzle. So what happens is that with a given, we can select as the reference, and often is used this reference, a cone with semi-half angle of 15 degrees. Not semi, with half angle of 15 degrees. This is our reference. That gives us some divergence loss. So what we like to do is to avoid having these losses by proper contouring of the nozzle. Of course, one can imagine that if at the end, at the exit, rather than having this direction, have something like this, possibly have at least at wall, I have something in the axial direction, I have a momentum in the right direction, and this would improve our performance. What we have to take into account in this discussion is that here within our divergence section we have a supersonic flow, and supersonic flow must be treated according to their properties. And so you cannot say that, okay, instead of having this cone, I just do something like this and I found my solution. So I just do something very abrupt. I change the direction here and I have my uniform flow in this direction. This is not, it's not what happens. So we have to remove this concept. We have to go towards something that can be achieved. And actually you can study, and probably you have done something about that, the nozzle shape based on the method of characteristics as a first, at least a first understanding. And you can imagine that if you have trot here, you could now consider an expansion and then a realigning of the flow that gives you a shape of this kind with expansion waves which are reflected here and in some way are left churning brought by these lines is compensated by turning of the jet. Here we don't go into details of the design of the nozzle by method of characteristics, but what you see is that from this kind of methodology we can actually have one-dimensional flow at the exit. So we can reach the ideal operating condition if divergence are the only loss. But this occurs with long nozzles. So different design options have been considered that lead to our usual bell nozzle that have this shape, more or less something like this. So what happens is that you still have some component in the radial direction that of course you don't have, and this is what matters more. You don't have uniform flow here, but it's less non-uniform than in a conical nozzle. And you can obtain the same area ratio in a shorter length than, for instance, a 15-degree cone. So, for instance, the same area ratio with a 15-degree cone would be here, or this length. So this is the same exit radius, and this is a 15-degree cone. So you see that we have obtained with this contour nozzle, or at least you can hope, and you can, we have not demonstrated it, but you can have, let's say, more aligned and shorter nozzle. So this is the reason why we prefer bell nozzle or contour nozzle to cone. This the design of the divergent shape, however, is quite important because, as I mentioned before, what is important here is the distribution of velocity at this exit section, and this will depend on how is realized this profile, because in fact what we are doing here is analyzing the exit condition to evaluate the internal forces, and of course forces will depend on how is shaped this profile. And so this kind of shape, for instance, will generate shock, will expand, will provide very low pressure in the first region because you continue to expand here, and so in the normal direction of in the direction of thrust you have very low pressure, and then you have a compression later, and this could be also leading to lower the ambient pressure here, and then recovering the ambient pressure through a shock in I'm pointing here. So we have strong expansion and then a compression due to these changes of curvature that yield that here we have a very low pressure. And this is the region where we have that the wall is perpendicular to thrust direction, so where pressure should more contribute, and here is more or less zero, if not negative, because for this compression we reach the adapted condition that was, for instance, the theoretical value for that area ratio. So you see that this kind of design could have some problem, and in fact this contour nozzle, of course, the design of this diverging shape is so important. And on the opposite side we have the converging part of the channel of the nozzle. So I mean now to focus on this part and up to throat, and this is not a problem. Any sufficiently smooth profile is okay. You don't have large consequences on the thrust generation because subsonic flow adapt easily to your design and do not yield to such a disturbed throat, let's say sonic conditions at throat. So, as I mentioned before, one problem is that of trying to adapt a first stage, or let's say a sustained stage, to vacuum condition, and there are different solutions that have been imagined, so different nozzle shapes that try to provide a better adaptation at for varying altitude than a conventional nozzle, or to control the flow separation. And so possible options are thus of controlling, as I said, flow separation. That means something like a dual bell nozzle like this one, where we have a discontinuity in the profile that allow you to anchor your separation here, or other devices with external expansion that allow you to adapt to the pressure value at different altitudes. And this is the case, for instance, of plug nozzle of aerospike, where we have, let's say, jet here and the central spike. And you have your jet. These are the walls. Okay, like this. And so here you have that this jet can expand according to the ambient pressure. It can expand to this value or to other values, or so on. We don't go into details also of this, but just to mention that there are these possible solutions, despite we have almost every, at least large rocket that has been built so far, only used Bell, the conventional Bell nozzle. But this plug, these are dual Bell, and these are plug nozzles, allow in principle to get a better adaptation behavior. Here we have two adaptation altitudes. Here we have, let's say, a self-adaptation up to a given altitude. So as to say that here for the dual bell we have two altitudes, so like you have something like this, and for the plug nozzle we have something like this. You are always adapted up to an altitude where you follow, let's say, the underexpanded behavior. So this is always CF versus Z. So now I would like to show you some images. Can you see it?
Sì.
So this is the Z23 nozzle. It's a solid rocket, and you see this is not optimized to have the higher thrust coefficient because of even if it's an upper stage, is Z23, and even if it's an upper stage, there is a problem in solid rocket, which will be mentioned later, that is the presence of solid particles that can impinge along the walls. So the turning back is not considered as dangerous. So if you see this in the vertical line here, a vertical picture here, you see that we have something which is slightly contoured. So it's not exactly a straight line, but you don't see a high turning back. This is, on the other hand, is the SSME, so the main engine for the space shuttle, space transportation system, and you have here a clear bell nozzle profile. So it's again a parabola, or a parabolic, let's say, roughly parabolic profile, but you can see here more careful design to obtain the best performance. And consider that this is an engine operating from sea level to vacuum. And then you see now some images of vacuum engines where you can clearly see not only the bell shape, but also the high area ratio that we are achieving. So this is the AVUM upper stage of Vega, and it's a vacuum engine, and you see the parabolic contour, let's say the bell contour, more precise, and also the high expansion ratio, as well as for a small engine like this, where we are careful to correctly draw the nozzle profile and consider a high expansion ratio. This is another one that you can see where we have a very high expansion ratio, and this is even higher. You have here an expansion ratio of 400 in terms of area. The exit area is 400, the throat area, or better, is 371, as you can see written here. So recall there was this 10 times factor, so it means that there are many thousand value lower. There is many thousand times lower the exit pressure compared with the total pressure. And this is something, if you see something like this, you understand that you are operating in vacuum. So about the underexpanded nozzle, we have drawn some expansion waves like this, and you see that here is in the bottom drawing is something that remains isentropic with compression waves, because it's let's say it's planar mild expansion in the bottom drawing, where you see that the expansion wave reflect as compression waves and reflect again as compression waves, and we have never shocks. We risk to have it exactly here. But in general, this, if you consider something if you consider also the axis metric contribution, and in general case, you always say when you have compression waves, you also realize the shock. And so you see in the top line here, you see the generation of a shock along the core of this underexpanded nozzle. And you see here clear an image that taken from the literature of an underexpanded jet. This is axisymmetric, and you see that the shock becomes evident. And you see also a macro reflection here that can be easily identified. And this is the underexpanded jet around Saturn V. So you see this big plume saying that we have reached, if not vacuum, let's say high enough atmosphere that pressure is low, and so the jet becomes very wide. In the overexpanded condition, we have the generation of shock here. Because of this overexpansion, we have no separation, and this shock can lead to a regular reflection or to a Mach disk or Mach reflection. So a regular reflection in E on top here, or a Mach reflection here. And you see this Mach reflection or Mach disk here very clearly. You see the overexpanded jet of the SSME, and you see here the shock. Well, you don't see the first part, but you see how it becomes hot after the normal shock, where you have a high velocity here, and we reach a high temperature and denser flow just behind the shock. Whereas in general, the jet of an oxygen-hydrogen engine like this is roughly transparent. So this is an enlargement taken from the right picture, and this is another picture where you can see that the the known shape of compression and expansions with diamond-like structure that occurs in both overexpanded and underexpanded jets. So this is a plot to say something about the shapes that we can select for different nozzle. We have the aeration on the abscissa and the length on the ordinate, and this length is non-dimensionalized with the throat diameter. So we have this reference, which is the 15-degree conical nozzle that you see here, and possible options. We have an ideal nozzle that allows us to have the one-dimensional flow at the exit, but is far longer, which is this one we see here on top. And we see that the contoured nozzle is shorter with the same area ratio, and that you can have also different options as clustering nozzles that allow you to have the same area ratio with a shorter length, and also even shorter is the case of truncated aerospike or expansion deflection nozzle that we have not mentioned here. Something more about this kind of nozzles will be part of the course of liquid rocket engines, as this performance-oriented nozzle design is relevant for that kind of applications. These are the couple of pictures of planar or toroidal aerospike nozzle. So with the expansion, external expansion, there is the jet here. You see here there is a conventional nozzle exhausting along this wall that allow you to have different pressure behavior as a function of the altitude on these walls, and so it leads to the side adaptation. So with this, we conclude the ideal nozzle theory, and we move forward to, let's say, to analyze the other contribution that we have to specific impulse, which is our thrust coefficient, characteristic velocity, our C star. So when talking about C star, of course, it's important. We see that the efficiency of our system depends directly on this quantity. We see that the thrust record that is related only to thrust coefficient, whereas C star appears in the...
Scusi, non sta condividendo lo schermo.
Grazie mille.
Prego. Grazie a lei.
Ora lo vedete?
Sì, adesso.
So, of course, the specific impulse is related to these two quantities. So we see that if we like to have a high specific impulse, we need high characteristic velocity. So this velocity tells us about the energy we have available to achieve a high exospeed. So of course, the high exospeed means high kinetic energy, and to reach high kinetic energy, we have to start with a given level of energy available. Pressure tells us how we can change, we can accelerate the flow, but at the end, the content of energy is related to the C star. So C star leads to the different kind, to the analysis of different kind of thermal rockets. In fact, different thermal rockets, the difference among thermal rockets is related to the way we achieve the desired value of, or the achievable level value of C star. We can achieve this C star by heating, by internal release of energy. In general, I recall that we have some internal energy as a starting point. We have something which is stored in tanks or as a solid or or as a gas, and it has some internal energy as the that characterize this substance. Then we can add some energy. We can add nothing, or we can add some chemical energy or nuclear energy. So, or energy from chemical reaction, energy from nuclear reactions, or we can exploit solar energy. So the first is nothing. We don't add anything to the original internal energy. So if we, with this, if we consider this case, we are considering the cold gas thruster. What we can do with chemical energy? We can use it to directly heat our fluid through combustion. That means exothermic reactions, or we can obtain some electricity. This is just to recall what we have said at the beginning. And similarly with nuclear energy, we can, let's say, provide heat in some way, or we can pass through electricity. And similarly for the solar energy. And we can put together these to get electrothermal rocket. Whereas for chemical, nuclear, and solar, we have chemical rocket, nuclear thermal rocket, and solar thermal rocket. So let's go to our goal, which is our C star values. So if you are not, we have this starting value, which is available in all cases, and typically it's not so high, and because it would be difficult to store at high temperature a gas, and the gas is not efficient to store because it occupies a large volume. So we don't expect high performance with cold gas systems. We expect that C star, which is in the ideal case, we have seen that would be RT over gamma, and of course the main quantity is this T0, and we don't expect high values of T0 in cold gas. So by definition, we are not heating the gas, we're just storing the gas as is, and so we don't expect high performance. All the other systems foresee something different, because if you don't accept to take the gas as is, it means that we are doing something to increase its temperature, and we are doing this by different means, which are chemical, nuclear, and solar. And what as we mentioned since beginning of the course, or we recall since the beginning of the course, we can get this energy that allows us to increase this temperature through chemical reaction, through nuclear reaction, through electric resistances, or through solar energy. But there is difference among these options, or there are, because we have that in case of chemical rockets, and also in theory also in case of nuclear rockets, we can get this heat directly inside the propellant itself. That means that compared to the case of solar thermal rocket or electrothermal rockets, where you have to provide, you use the energy to get heat, and through this external energy you have to heat your propellant. In case of chemical reactions, and in principle also in case of nuclear reactions, you could or you can release this energy within the propellant itself. It's something which is inside the propellant, if you have just to make it available for heating. In fact, what is important is that in this case, you have not to realize external devices to heat the propellant. Whereas this is the case for solar thermal rocket, nuclear thermal rocket, and with external heating, and also electrothermal rockets. Whereas for chemical rockets and, let's say, nuclear thermal rockets with inside energy allow you to have less external mass that is required to heat your propellant, and so they are able to generate very high thrust to weight ratio. So you recall that another important property of a rocket is the thrust to weight ratio, that is different depending on the specific way we are realizing our thrust. So the higher thrust can be achieved when the energy is released within the propellant itself. And this is for sure can be obtained for chemical rockets, and in principle, as I mentioned, can be obtained for some case of theoretical nuclear rocket. Anyway, we are used with the exploiting of chemical energy or chemical reactions to have high temperatures, to have combustion in many applications on Earth. And so, of course, this has been also the first kind of energy that has been supposed to be used for rockets. The reason is that, however, being this energy released internally, being in the sense that is part of, is stored inside the propellant itself, allow us to have a high thrust to weight ratio, relatively cheap or easy realization. And well, it's also important thing is that it allows to get to reach our objectives, our goals, because actually with chemical propulsion we achieved all the required mission for space application. That means reaching the orbit and moving from one orbit to another, and reach the moon, for instance, and so on. So this is just an introduction of this most important part of rockets or rocket engines or motors, which are the ones which are based on chemical reactions. So we talk about chemical rockets, and this will be the topic of the next classes. So we focus on this family, and we will only mention at the end of the course the other options that we have. And the reason is that most of rockets realized so far, the ones that allow us to get access to space, are chemical rockets. So it's important to have a knowledge of them. Of course, cold gas rockets are often considered part of chemical rockets, despite there is no reactions that has to be considered for them. So to talk about chemical rockets, we have also here, as we have done before for when we started to talk about thermal rockets, we have to record some basics of, let's say, chemical reacting mixtures. So the first step is to see a matching between what is happening here, chemical rockets, and what is our goal, our C star in this case. So in the release of energy, focus is on the C star, whereas in the expansion it was on CF. So the thrust coefficient was thermal rockets. Now, once you specify the kind of rockets you are talking about, you should first focus on the C star. So what is the relation here? And with the expansion we have studied so far of thermal rockets, the relation is that chemical reaction will release a mixture of gases. Let's call them combustion products that will have some kind of properties. Gamma, capital gamma, R, and T0 that will fill this expression for C star. So this will be the property of a mixture of gases, because, as I said, these are the combustion products, the products of a chemical reaction. We have somewhere we have stored our reactants. They will burn, will release heat, and will decompose and rearrange their species. And at the end, we have this mixture that will be represented with these properties. So we have first to record something about mixture of gases. And we can refer, as this will be always the case because of the high temperatures, at least as far as we are talking about the expansion within the nozzle, we have a temperature high enough that we will always talk about perfect gases. So we have to consider now a mixture of perfect gases and define some of their properties, or recall, better than define, some of their properties. So we have inside this mixture a given number of species, let's say n species, and in this mixture we'll have a mass, will be some put together a given amount of gas, which will be made by the sum of the mass of each gas that compose the mixture. So we define this way: the mass of a mixture will be the sum of the mass of each species making together this mixture of gases. About temperature, we introduced the thermal equilibrium among species. That means that all species have the same temperature. This is something that is achieved in a very short time And so we can always consider that we are in thermal equilibrium for our applications, or we will always consider these. There are special cases where this is not the case when we have chemical reactions, but this will not be, this is a very special case, and does not affect the overall conclusion that we can achieve. And then we have pressure. To evaluate mixture pressure, we resort to the Dalton's law. Of partial pressure. Let's say that the pressure of the mixture is the sum of pressure that each species will have if it will be the only species present in the same volume. So this is the definition of partial pressure, and then the total pressure, or the overall pressure, better, to avoid confusion, will be the sum of the pressure of each species. Then we also introduce the number of particles. The overall number of particles will be now, allow me to I changed symbol with this one. Number of particles, this calligraphic can, and will be N1 plus N2, the number of particles of each species. Will also be something that characterizes this mixture. And if we introduce, we have introduced already, and we all better again, we have already recorded that we have this Avogadro number that tell us about a fixed number of particles that allow us to consider the let's say number of particles of interest for macroscopic applications through the number of moles. So the number of moles is the number of particles divided by the number of particles that are present within a mole, and which is a fixed quantity, and it is 6×10 to 23 for if we are considering gram moles, or 6×10 to 26 if we are considering kilogram moles. So this can be gram moles or kilogram moles. Oh, sorry, kilomoles. No, kilogram moles. It's okay. So, and this is shortened with kilomoles. This is not 1000 moles, but it's 1 kilogram mole that corresponds to the quantity of matter. Let's say the mass corresponding, which has a mass corresponding to the molecular weight of the species we are considering. The mass in kilograms, mass in grams. So with this, last step is to recall that we are considering perfect gases, and so for each of the species there will be immediate gas equation P equal to nRT with universal gas constant, and if I sum over I and IRT, it means sum Pi is P, and so sum Ni is N, and so it's also valid for the mixture, the same relation. So we have that being the sum of partial pressure equal to the overall pressure, and the sum of number of moles equal to the number of moles of the mixture, we have that the same relation applies also for the mixture. So we have seen this, and we will continue tomorrow shortly with other definitions, and then we will consider, we should also consider the introduction, let's say, of heat exchange to the reaction in perfect gas mixtures. But this will be done tomorrow. I will stop here for today.